So take a few minutes right now. I'd like you to do this. Put this in your calculator. If you set it up on Zoom Decimal, you'll be able to see the different types of discontinuities more clearly. All right. This is not such a big deal, but if you look at it, you'll learn something from the graph here. When you do Zoom Decimal, it uses these numbers because that it divides up into the number of pixels. I think there's 94 or 95 pixels across. There must be 95 pixels across because you need one for 0. But so if you do 4.7, 4.7, that's 9.4 plus 1 for the middle. It makes each pixel 0.1, right? That's what that does. It doesn't matter vertically because it's calculated values. If you graph it, then I'm hoping we can see what we're supposed to see. Whereas it's over there. Yeah, actually, I didn't need to go that high, but at least it gives you this other part of the graph. Okay, there's that missing value there. Remember, it looks like this with a break. In reality, it's one single missing value, like they're infinitely close together. If I graphed it on that other software, you don't see those things because it's so much higher resolution. It's calculating far more values than this is. This is only calculating a value every pixel. So it's only calculating 95 or whatever values across. And it knows that there's nothing. It's undefined there, so it just leaves that pixel off. If you wanted, you could. I mean, again, make the connection to the function. There's something happening at -3 and something happening at +3. Okay? There is a removal discontinuity at x equals 3. And there's also there's an infinite discontinuity. Oops. You can't take away the infinite discontinuity by playing around with the function. You can take away the other one. If you were to take this now and simplify it, or do what's done down here, which is change it into a piecewise function where it's this everywhere except for 3, and then at 3 it's what it's supposed to be, 10/3, 3.333. If you go back to the calculator now and you trace, you find that as you get closer to this, the value is going to get closer to 3.3333. Okay, you can't. There's no point. It's no value at that point. It's undefined. But what it should be is 3.33. You could zoom in and check that a little more closely, if you want. The way you can find that value is simplify this. If you wanted to factor the top there, what you're going to find is on the bottom of this thing, x plus 3 and x minus 3. The fact that at x equals 3, there's a removal discontinuity, that hole in the graph, this thing is going to have a factor of x minus 3. This is going to be x minus 3 times something. We could go through and divide this out and find out what it is if you wanted to. But it's going to have, I don't want to bother doing that, so I'm just going to do it the way we've done it down below here is this. Look at what that, if we want to go through and find the limit, we actually have to divide that. Do you remember how to do long division from grade 10 or 11 or whatever? We're not going to do that very often, but this is supposed to be x squared. I mean, we can figure it out just by trying here, I'm sure. What is this got to be here? It's got to be plus 2 on the end, right? I think. And what's got to be in the middle here?
Where is this?
I'm just trying to factor the top of that thing. It's cubed, right? It's not squared. That's the problem. Really, if you wanted to factor it, you'd have to do long division like this and say x minus 3. Remember doing this stuff? X cubed plus 0x squared minus 7x minus 6. It's not going to be required all that often, but I want to remind you of that in case you have to resort to that at some point. I don't really care if you find something that, finds that for you. I'm not looking for this kind of stuff. If you know what it's equal to, that's what I was thinking we could just figure out what it's supposed to be there. If you divide this in, you get x squared, then you get x to the third minus 3x squared. You subtract that, you get 3x squared, you bring this down. You go x into 3x squared goes plus 3 times. And they go 3 times that is 3x squared minus 9 x, yeah. Negative 7x minus negative is like 2 plus 2. And then you're going to have a remainder or whatever, right? What do we have here now? We have 2x minus 6. X minus 3 into that goes 2 times. It's this. It's plus 3x. It doesn't come up that much. It's not going to be where we're testing this sort of thing. If I really wanted to test you on this, I would give you one where the top was just a quadratic and you could just factor it by looking at it. I don't want us to get hung up on all the pre-calculus math. But if you ever do have to factor a cubic, you might want to look back at your long division. And if you need that, you just go to the internet and find out how to do it. It's not that hard. I'm sure you were good at it at the time. Okay? Anyways, the fact that, and plus you can use your knowledge now that if it has a missing value if it has that hole in the graph at 3, you know that this is going to be one of the factors. It has to be a factor. If you find that it's a graph like this at 3, you know that x minus 3 is going to be a factor of the top and the bottom. That's the only reason it happens like that. If this was something else like plus 3, then this would go, it would be an asymptote at that value. When it's a missing value, a hole in the graph, it's when it has a common factor on the top and the bottom. All right? What's that? Not right now. I really don't want to get too far off the track here. I mean, I don't want you to lose track of the idea here is that if you have a function that has a missing value like that, you can fill it in either by simplifying it. If you graph just this now, it would look exactly the same as that other function, except that value would be filled in. Okay, it wouldn't have that hole in the graph at 3. The other way you can do it is, if you happen to know what the value should be, you can just define it as a piecewise function and say, well, it's this everywhere except 3, and then it's that value at 3. The way you can find that value is with limits, right? I mean, the limit of that f of x, the original function, as you approach 3, of this x cubed minus 7x minus 6. This is stuff we did in the past days here. If you want the limit of that, that's going to be the same as the limit of once you simplify it, right? X squared plus 3x plus 2, x minus 3 over x plus 3, x minus 3. Those limits have to be the same. If you're just algebraically changing things, they have to have the same limits. The reason you can't evaluate the limit right off the bat because you can't put in 3 into that function, it's undefined. Whereas if you simplify it, then you can plug in the value. As soon as you make it x squared plus 3x plus 2 over x plus 3, now you can plug in that thing. Okay, now you can sub it in. Whereas up here it was undefined at 3, right? Undefined at 3. This is what we learned or looked at before. If you put 3 in there, then what do you get? 3 squared is 3 squared plus 3 times 3 plus 2 over 3 plus 3. What do I have there? I have 20 over 3, 10/3, right? That's where that value comes from. If you have a graph that has a missing value like that, you can algebraically simplify it. So 20 over 6. Calm down. That's the. You're laughing at my mistakes, eh? So when you hand in your test, I'll do the same thing. Mike, what were you thinking? It's 20 over 6. I can't believe it. You wrote 20 over 3. I read the scale wrong. All right.